I'm going to talk about GGFAST, our framework for automating generation of flexible network traffic classifiers. Network traffic analysis is the backbone of security in enterprises today, and it encompasses tasks such as L7 protocol identification or mode of use identification to understand what a protocol is doing. And to design a useful framework, we have 4 key objectives in mind. We want the classifier to be accurate. We want it to be interpretable, so we can understand its decisions and trust it. We want it to be generalizable, so it can be applied to any labeled traffic. And we want it to be efficient. But if we look at L7 classification specifically today, none of the solutions that we have are really good on all 4 fronts. For instance, port-based classification, which was the first solution for L7 classification, is no longer accurate or generalizable because many applications don't use the same port all the time. Payload-based classification, which is still the main way of identifying protocols today, works well, but isn't generalizable to encrypted flows. And machine learning-based solutions, usually using deep learning, work well, but aren't necessarily always efficient, and most importantly, aren't interpretable. We don't understand why they make the decisions they make. And so with this in mind, we designed GGFAST, our proposal for an automatic derivation of fast, accurate, and interpretable classifiers for any task with labeled data. On top of this, GGFAST is transferable to encrypted data, meaning we can train it on clear text data and still apply it to encrypted data, even if it wasn't in the training set. And it only relies on sequence of packet lengths and not on the content that flows, meaning it can be applied to any type of traffic. And the key insight behind GGFAST is that protocols induce predictable patterns of sizes and sequence of lengths. And if we look at these sequence of lengths, we'll want to find motifs that we call snippets within sequence of lengths that are characteristic of each class of traffic. When we say characteristic, we mean motifs that almost only occur in traffic of a particular class. So if we look at our whole GGFAST framework, which is based on, the name is based on the 6 steps, it starts by grouping sequences of lengths, then gathering snippets, and then goes through a bunch of steps to finally get a naive-based traffic classifier. We don't need to understand all the steps for this talk. What we need to understand is that with an input of any labeled traffic, we get a very simple naive-based classifier that only depends on the presence or absence of snippets, these motifs that we find in sequence of lengths. And so we'll spend the rest of our time trying to understand what a snippet is, because that's key to the intuition behind GGFAST. So let's start with an example. Here we have a POP3 session, which is of course not a real one. And we look at its packet sizes from the server and the client and take that and transform it into a sequence of lengths, where a right arrow is indicative of a flow from the server to the client, and a left arrow is indicative of a flow from the client to the server. Now, taking this sequence of length, we're going to understand what a snippet is. Snippets are made of 3 elements. The first is the motif, which is the sequence of length and length ranges that we find in a sequence of length. So let's start with an example. Motif with a client's packet of size 6 and a server packet of size 51 matches the blue sequence here. However, GGFAST also supports length ranges. So for instance, a client packet of size 6 followed by any server packet matches all the red sequences. And the ability to support length ranges automatically, meaning we don't have to specify them ourselves, means that GGFAST can capture a wide variety of behavior that can be exhibited by complex protocols. So a snippet is, before anything, a motif, but it's also an anchor that specifies the position of the motif within the sequence of length. An anchor can be relative to the start or the end of the sequence, meaning it's a motif that's starting the sequence towards the end, but can also have a star value, which means it can occur anywhere. So to give an example, consider a motif of a packet size 6 from the client. In red is the match for anchor 4, starting at 4 after the start of the sequence. In blue is the match for anchor -2, occurring 2 packets before the end. And in green are all the matches for any anchor. And so with these two characteristics, the motif, the anchor, we can already characterize a lot of different activities. But as we said earlier, our classifiers were based on the presence or absence of snippets. And so it's important to have a negation flag to be able to characterize the absence of a motif instead of the presence. And so now that we know what a snippet is, let's go back to our example. And we're going to find two snippets that are characteristic of POP3. The first snippet is the motif of client packets 6 to 8 going from the client to the server, occurring anywhere in the session. This is indicative of small POP3 client commands, such as stat, list, or delete. A second indicative snippet is packet size 6 from the client and any server packet occurring 2 packets before the end. This is characteristic of the connection shutdown in POP3. And with both these snippets, we can build a pretty good characteristic of POP3 that doesn't really occur in any other traffic. And what GGFAST does is that it takes this manually crafted example and actually does this automatically for any traffic you throw at it. So now that we've seen how GGFAST works, let's look at how well it does. Our first evaluation is done on 1 day of traffic from Lawrence Berkeley National Labs. And the task here is L7 classification, so understanding which protocol is being used over 14 different applications. And we only trained on 0.1% of the data set. And what we found is that GGFAST equals the state of the art in printml, however, uses 100 times less features and makes explainable decisions thanks to the snippets. And actually, if we take GGFAST features and nprint features and combine them, we can train a classifier that goes even further and gets to 99% accuracy, because our explainable, interpretable features are orthogonal to the features that nprint uses. Our second task is classification of SSH and RDP authentication mechanisms on 2 months of a university traffic. And we find that we get near perfect accuracy, even though the traffic is encrypted and only relying on a handful of snippets. So this shows how GGFAST is competitive with the best techniques, yet is still interpretable and easy to use. However, that's not all. GGFAST supports what we call the encrypted transform. What we noticed is that encryption hides contents, but not lengths. The length for ciphertext is deterministic given the original packet length. So what this means is that if we take model trained with GGFAST that relies on a set of snippets, the same model, but change the snippets to their encrypted sizes by applying the cipher, but just on the sizes, not on the contents, we can have a model that works on encrypted protocols, even though it's never been trained on encrypted protocols. It's only been trained on clear text. And when we tried to do this, we have a first experiment where we took dataset A and replayed it over an SSH tunnel, keeping the 14 unique protocols. And we only see a 5% loss in accuracy, even though we've never trained on any of these encrypted protocols. Another example we tried was to train a classifier on SMTP recognition compared to other protocols and convert that to SMTPS, not SMTP with start TLS, but SMTP over TLS. And what we found is that we only had a 0.5% false positive rate. So we were able to uniquely identify SMTPS. And in 80% of the cases, we could still detect SMTPS. And if we dig deeper into these 0.5%, we realize that most of the errors are actually POP3 over TLS or IMAP over TLS. So our classifier can actually recognize email traffic, and the errors are actually understandable. So to summarize, GGFAST is a framework for automated feature engineering and network traffic analysis that produces state-of-the-art classifiers with explainable decisions, which can be transferred to encrypted traffic without any additional training. Thank you for your attention.